Okay, well, hello everyone. We're back. It's now Wednesday, and last time we went over the stuff for for derivatives in the shapes of graphs. It's hard to keep your thought here because there's so many distractions, right? Brain just goes. If you're in this class, please jump into Discord. And the chat channel we are on is the 2020 03 25 11 a.m. if you want to ask me questions. Are there any questions before we begin? I asked this in audio chat just a moment ago, and there weren't. But is there anything anyone wants to ask me now? Okay. There was a question about the notes for scanning for problem set 10. Yes, you're supposed to scan your notes. You can take a picture of them with your phone, but please use a PDF program so the iPhone does it directly, or you could use the something like PDF. I don't remember what the scanner software is, but there's several scanner softwares you can use. If you take a picture with your phone and then convert it to PDF and then upload it to Gradescope when you're done. So that was one question about the thing. The other question that's being asked right now is, can you redo quizzes? The answer is not yet. I'm working on it. But hopefully that capability will be up next week. We're playing with it this weekend when we play with Proctorio and see what we can do about that. I want to be able to retake quizzes. I want that to still be a thing. I really think it helps people to retake their quizzes. And it lets me ask slightly harder quiz questions because then I know you have a little bit of a cushion. But I want that to work, but we haven't got it working yet. So work in progress on that one. Any other questions? Cam Skater, yes, that was it. Thank you very much. Someone in chat just mentioned what it was. By the way, I'm not mentioning your names, not because I want to be rude, but because Twitch is public. And so I'm trying to protect student privacy, but not mentioning names. Any other questions, comments, issues, suggestions, and thoughts? Okay. So last time I gave you a quiz, so let's go through it. So Fermat stationary point theorem. First of all, how do we feel about the quiz right now? 1 to 5. Let's see if I can do this again. 5 poll. 1 to 5 quiz. So how do we feel about the quiz? 1 to 5. All right. So okay. So let's go through it. I got some shrugs. I've got some other stuff. The one thing that's weird is that it doesn't let me. I don't know why it doesn't let me see these other statistics. Okay. Well, anyway, let's stop being distracted by the cool stuff. And let's go back to this. So, the question. So, Fermat stationary point theorem. Do we all feel pretty good about that one? By now, this is just preamble. That's why I made it small. If f is differentiable and f has a local min or a max, then f prime of that point equals 0. 1 to 5. How do we feel about that? Oh, I can't do that again. Oh, nope, I can't do that again. Sorry. I need like macros for this. Question number. Okay. So we feel pretty good about that, this idea. Okay, so the next question here. So I wanted to find the inflection point, and this is fairly similar to one that we've already done, where what I was doing was I was looking for the min or the max. Because in essence, that's kind of what I'm doing. I'm looking for local mins and local maximums on the derivative. Because those are the inflection points. So let's talk about it. So my first thing I do is I take the derivative, and then I take the second derivative. And then I set that second derivative to 0. How do we feel about those first 3 steps for this? Let's see. Taking derivatives. So how do we feel about the fact that what I want to do is I want to take both derivatives and I want to set the second one to 0? It's kind of the process. Okay. All right. So I do that, and then I come up with a suspect point at x equals 4. I don't know that there's an inflection there, but there might be, right? Because that's a place where the second derivative equals 0, or the second derivative doesn't exist. Of course, there's no place here. We got a nice little polynomial. The second derivative doesn't exist. By the way, if you decided to take the quotient rule here, you could. If you view this instead, though, as the you could have done the quotient rule. You would have wound up with one of the terms going away. It's much easier to just view this as 1 over 12 times x cubed and do it that way. Because that's just a polynomial that just pops itself off. But anyway, so I suspect I have one at 4. So I'm going to stick 4 up here. Now, if f double prime is negative, that means f is concave down. If f double prime is positive, that means f is concave up. And I want to make sure that I've either gone from concave down to concave up or concave up to concave down. Because there are functions, x to the 4th being a perfect example, where I'll wind up with the second derivative as 0, but where I don't have an inflection point. Okay? So I need to check to make sure I have an inflection point by checking both sides. Okay? So my test points are going to be 0 and 6, because 0 is between negative infinity and 4, and 6 is between 4 and infinity. Now, there's a theorem called the intermediate value theorem that says that I can't go from negative to positive without crossing a 0. How do we feel about that, 1 to 5? About the fact that in order to change from negative to positive, the second derivative would have to cross 0. So in order to go from concave up to concave down, the second derivative has to be 0. So there's the question. Can I, how do we feel about that concept? Okay. So the question is that if the second derivative, I can pick any point then in my interval. As long as I don't cross a 0, I can pick any point and do test values for negative and positive. So here I picked 0, okay, because, 0 is a nice, easy thing to work with. 0 over 2 is half of nothing is nothing. Minus 2 is negative 2, and negative 2 is less than 0. So that means on the left, my second derivative is negative. On the right, I do the same thing. I pick a point, f double prime of 6. 6 is a nice little number. 6 over 2 is 3. 3 minus 2 is 1. And I wind up with something that's positive. So yes, so the second derivative is positive. That means the function is concave up over there. So yes, I do have an inflection point at x equals 0. Okay? Technically, the answer to this problem, because I asked for the inflection point, I would need to find the y value for x, right? So I plug y back into the original function to get that it's negative 32 over 2. I don't really care. The important concept is that you found the x value. Now, someone is about to ask in chat, what about the test? Go ahead, finish typing it. Okay, well, someone would have if I just didn't embarrass them. Oh, come on. You could finish your thought. I don't know so the original version of the test has to be totally rewritten now. And the reason why the test has to be totally rewritten is because we wrote it at the beginning of the semester with the idea that we'd be actually having an entire semester together. But now we're going remote, and so we're rewriting the test over the weekend. So the test we originally wrote, but originally the test asked for just the x value. What it continues to ask for will be another issue. But just as a technical thing, and I'll warn you about that, by the way, if the test does change its questioning. But, you know, I really only care about the x value at this point, which is completely different from the absolute min and absolute max, where I only cared about the y value, and that's because we hate you. No, not you in general, you in particular. So, just kidding, I love you. Why is there an inflection point at x equals? Because I am an idiot. Because I already fixed it once on the previous one, and for some reason I didn't fix it on this one. Sorry about that. The correct answer is there's an inflection point at x equals 4. I hope it's correct on the previous one. Okay. Well, if it's not, they're all going to be nicely confused. Anyway, so technically the point is for negative 32 over 3, but is it negative 32 over 2 or negative 33? Why does this say 2? No, I want the negative. There we go. Anyway, any questions about that? Oh, yes. You have to type it all out. No. So there's a question about, yes. So, well, you have to type it out. And this question about Factorio. Yes, everyone despises Factorio. We are trying to make it work so it's not so despicable. We're trying a couple different things. One of those things is probably going to be that we're going to, excuse me. No, I don't have coronavirus. At least I don't think so. I do have oak pollen allergies, which, you know, are things. But one of the things we're trying is that we're probably going to have an answer sheet that you print out in advance. And then, and Factorio is like a pain, but we kind of need it in order to do the integrity of the test. But what's probably going to happen is you're going to hold up the sheet of paper and say, and show that it's blank when you start. Exactly how that's going to work, what's going to happen there, I don't know. I do know that Factorio is despised and hated everywhere, and I also know that in one sense we don't really have much of a choice. It's the tool that we have. And other times we do have choices. You'll notice that I'm not using the tool that the university gave us for doing lectures because I think this is better. So if someone's got a better tool to ensure the integrity of the test, I am all ears. I'm all headshots at the moment, but I'm all ears. Any other questions? Okay. All right. So one of the advantages of doing this is now that I have this nice little chart, I've now shown all my work for concave up and concave down. So it's concave up over 4 infinity. How do I know? Because the second derivative is positive. So I say C chart. Same thing over here. I say negative 4 infinity to 4 C chart. Okay, 1 to 5, how do we feel about that? Dadgummit, now I'm copying and pasting the 3. The answer the question that's about the printing the test. Yes, you will be printing out the answer sheet, but we're going to give you the answer sheet way in advance. So even if you're normally doing the quizzes on an iPad or whatever, we're going to give you the answer sheet in advance. And even if you can't print the answer sheet, please try to print the answer sheet. But even if you can't, what we're going to do is let you use a blank sheet of paper, several blank sheets of paper. But you just have to, like the quiz, you have to keep them in line. And we'll go over that when we get to it. I know everyone's concerned about the thing. If f double prime is positive, then it's concave up. And if f double prime is negative, then it is concave down. Yes, that is exactly what's going on. So negative gives me frown, and positive gives me smiley face. Okay. We're positive about our graphs, not positive for coronavirus, right? That would make us sad. Anyway. Okay, so the graph of the derivative, the next question. Now, I saw a lot of them already. I've already graded a bunch of them, and I saw, well, partially graded them, and I saw many people thinking that this was the graph of f. No, this is the graph of f prime. How do we feel about the fact that what I'm looking at is f prime, its graph, and what I'm asking questions about is f. So 1 to 5, that is f prime. Okay. So the function I'm looking at is f prime, not f, f prime. Okay? And I'm asking questions about f. So instead of, if I thought about this, looking here on Desmos at this function up top, okay? Let's let this be f. And let's let this be f prime. Now, I'm asking questions about this function here, but I'm not showing you that graph. The graph I'm showing you is this one here. Okay? So the graph I'm showing you is f prime. Well, notice up here, if f prime is positive, right? If the slopes are positive, okay? If the slopes are positive, like I'd have to do it like this for you to see positive, right? If the slopes are positive, that means my function is increasing, okay? So this is where this tells me, this right here, the derivative, f prime, tells me the positive, right? Or it tells me the slope of the graph. So right here, you'll notice that f is increasing all the way to 2. That means that f prime is positive, is greater than 0, is above the x-axis. Likewise here, between 2 and 4 on this graph, the derivative is below the x-axis. The derivative is negative. That means that the original function is decreasing. Okay? So here, if I come back here, what intervals is f increasing? Well, the question is, if over what intervals is f increasing, then the question is, over what interval is f prime positive? Okay? Because that means that my slopes are positive, and that means my function itself is increasing. Okay? So how do we feel about that, 1 to 5? Oops. That should be f prime, not f semicolon. Okay. So it's a little tricky. Okay? So if I remember these relationships, remember these things. If f prime is positive above the x-axis, then f is increasing. What's more, if f prime is increasing, right, if my slopes are getting bigger as I move left to right, that means my function is concave up. My slopes are getting more positive, that means my function is concave up, right? Because here the slope's negative, 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 less negative, but less negative, less negative, more positive, more positive, more positive. Okay. So over what intervals is f increasing? Well, negative 2 and 3, 4, because that's where f prime is positive. Where's f decreasing? Well, from 0, 3. From 0 to 3, open intervals, and that's where f prime is less than 0. So how do we feel about part A and part B? 1 to 5. Okay, so we're a little iffy on that. I will have the normal, not only will I have office hours during the normal office time, I will also have the 5 p.m. Problem set. I'm sorry, problem session tonight at 5. So that'll be online on Discord as well. Not on Twitch, but on Discord. I'm going to also have the problem, the problem help session. So let's go over this then. All right. Same thing here. Over what intervals is f concave up? And again, f is concave up where f prime is increasing. So let's look at that again. Right, here's f and here's f prime. Okay, so where this function is, the slopes are getting, more and more positive. Right, here the slope's negative, here the slope is less negative, here the slope is even less negative, and they're flattening out, and then they're getting more positive over here. That is where f is concave up. So if you look at the derivative, that's where the derivative is increasing. Okay, so the derivative is increasing everywhere right of 3. The slope of the derivative is 0 here at x equals 3. And because the slope of the derivative is 0, and because I have a min in the local min in the derivative, that means I have an inflection point. Okay, and here now the slopes after this point 3, there it is. After this, the slopes get more and more positive, right? They get less and less negative, and then more and more positive. And that means that, and you can see that here, the derivative is increasing. The slopes are increasing as I move to the right. Okay, so how do we feel about that? 1 to 5. Okay, so again, a little bit of confusion. We're a little bit fuzzy on this. Okay, so the question is, it depends. Are you looking at f or are you looking at f prime? When f prime is above the x-axis, then f is increasing. Not when f is above the x-axis. F can be below the x-axis, but increasing, right? But it's where f prime is. F prime is above the x-axis. Does that answer your question? So again, it's not when f is below the x-axis, it's when f prime is below the x-axis. And think about the slopes of these tangent lines. And I know it's a little confusing, but after playing with it a while, you'll get it. You can get it. And there was an activity that I would have done in class had this whole shindig not happened. That kind of firms this up. And I'll try to remember to post the activity. Let me make a note of that. Post activity. Maybe I'll make that part of next week's problem set. Post activity on derivatives and shapes. And I'm sorry that Twitch is lagging on you. You should be able to, I don't remember if you can, use the closed caption setting. But because I think I set it up to do closed captions, but I'm not 100% sure on that. If I didn't, I'm going to start working on that again. Any other questions? Okay. So that's this. I've got these two things. Now, the other question you're going to have is, do I include this 0? And the answer is yes. I want to include that point because here I'm still decreasing. I'm decreasing over that 0. Even though the first derivative is 0, it's still decreasing. And the second derivative is 0 there as well. Any other questions? Okay. Name one thing you found memorable from our last class. Nothing. Working arc. Any questions, comments, issues, suggestions, thoughts? Okay. So how do we feel about that now, 1 to 5? How do we feel about this quiz, 1 to 5? Better, worse? Okay. All right. So again, we can go over it some more during the problem set today. Also, if you watch the video from the last one, I may have done slightly different explanations, so it might have made you feel better. Some people are saying the last question is confusing. You need to keep track. You need to look at what you're looking at. So you're looking at f prime, and I'm asking you questions about f. And so, there was all this subtle stuff to say that you were looking at the graph of the derivative, like right here where it said the graph of the derivative in bold, where it said f prime of x, shown above, to answer the following questions about f. And then I made this little subtle thing where it said f prime of x here, and then this was subtle, and then I told you it was similar to the 2 problems in the textbook, one of which I believe has answers in the back of the book. Now, that does not mean that this problem was easy, and it didn't mean that that was not an easy mistake to make. And the reason why I always put this on a quiz is because if this shows up on a test, and I like these problems, now whether or not they still show up on the test after the weekend is another question. But I like these problems, and if they show up on a test, I want you to make the mistake here on the quiz and not on the test itself. Now, the next question is, how do you do quiz retakes? The answer is, I don't know yet. I'm still working on that. Hopefully that problem will be solved this weekend because I really want to do quiz retakes because I believe strongly in them and they really help. Any other questions, comments, issues, suggestions, thoughts? Okay. So let's go back. So today we're going to talk about something that's it's sort of assumed in the, which is a shame. It's sort of assumed in the book that you've seen this before. And that's proofs by contradiction. And I'm not happy about that the book assumes this. The big version of our book, right? We have the essentials version, right? There is a big version of this book. And the big version of this book actually has an entire section on this, or an appendix or something. I left my big version of the book at USF, and now Jane Castor doesn't want us to leave the house, apparently. So I may be able to go get my book, and I may not. Anyway. So the yes, so the I'm sorry, I'm trying to watch chat at the same time I'm trying to do this, and it's extremely distracting. What I should do is minimize chat. What I wanted to do was have a TA here to read the chat, and maybe I'll be able to get that set up so that the TA could tell me when to do things. But it's extremely distracting. Anyway, so back to what I was doing. Not that I don't want you to ask questions. I want you to ask questions. I want somebody there to filter the questions for me and draw my attention. Have a little blinky thing that says, hey, someone's asking a question that you should answer, and then I'll turn my head when I'm done. But yeah, it's not. So, it is what it is. So anyway, the book has this whole big section, and this book kind of assumes that you've seen it. So he does proofs by contradiction without actually explaining proofs by contradiction. So I wanted to take today, and I wanted to actually, explain proofs by contradiction. I'm not the only professor that does this. Most of the instructors are going to kind of mention it in passing. I'm going to make a whole section out of it. I'm sure that another instructor will make an entire long 2-hour video about it. And someone had asked in chat if I could post the videos from the other instructors. And my answer is if they give me permission to do so, I will be happy to do so. I will give them permission to view mine as well. Not that they need permission. I mean, they're just on Twitch, right? So I haven't gotten an answer to that question yet. But going back, so not everybody's going to cover it. I'm going to cover it. It's one of those things that 30% of you are going to absolutely hate and despise. 20% of you are going to go, oh, that's the coolest thing. I saw it back. And then, the rest of you will be like, you know. Do you need it for the test is, of course, the next question. And the answer is, you remember on the last test how there was a way to get away with not doing a linearization problem, right? There was kind of a proof and a choice. It's sort of like that on this test. At least it was. Whether or not it's still like that is another question because we have to rewrite the test. But it was sort of like that, right? There was a proof that you could do by contradiction. You could do it by another thing. You could do it a couple of other different ways. The contradiction proof was the cleanest. But you could have gotten around it. So I'm going to do it. So how do we feel about this project? The fact that I'm actually going to do proofs by contradiction. How do we feel 1 to 5? All right, so I've got some of you are bought in, some of you are like meh. Let's just do it. And as I said, you can get away without doing it, but it's really clean, it's really cool. And if you're going on in math beyond Calc 1, you're going to want it because you're going to want to see it because you're going to want it in your toolbox later. So let's go over it. So again, last time we went over the change of the change. I am going to come back to section 4.3 because I had all these technical issues. I'm still having technical issues today with my tablet, which is why I'm mostly going over these notes and text. I anticipated it this time, and I made text notes to go over, and I will have drawing capabilities hopefully back in just a moment. But I did order a new tablet off Amazon. That should be here on Friday. And I also ordered a cooler for the new tablet on Amazon. So hopefully that will solve the overheating problems with the tablet. Anyway, so let's go ahead. That's enough about all the stuff that I'm doing here. Let's go over this. So the plan on today is to go, and we're going to do proofs by contradiction. It's in the pre-calc book, which I, of course, left in my office. It's also in the main book. I'm talking way too much over this. We're going to go over Rawls Theorem with the proof. It's got a nice contradiction proof. There's another proof in the book that you could use instead. And then we're going to start the mean value theorem. I didn't finish it last time. We're probably not going to finish it this time. On Friday, you're going to go over the intuition behind the mean value theorem. Now, 2 reminders. There's a problem session at 5 p.m. this evening. And there are 2 pre-assignments for this week. One, get on Discord. Most of you are already on Discord, but it also gives you instructions on what you need to do. And the second is the normal pre-assignment. Are there any questions about that? Okay. So the big idea behind proof by contradiction is the following. In mathematics, a statement cannot be true or false. A number cannot be both positive and negative at the same time. Okay? So if we wind up with that kind of situation, if I wind up with 2 statements that contradict each other, okay, the statement that led to the contradiction must be false. Because I can't allow things like this. If I allowed things like this, our entire logic system would break down. Okay, which is a little different than we actually normally think of in the real world. In the normal world, we think, sometimes this, sometimes that, and blah, 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 blah. And statements can kind of be true and false at the same time. No, in math, it's yes or no, true or false. So if you take a statement and you wind up with a paradox, you wind up with 2 things that contradict each other, the original statement must be false. Okay? So the biggest famous example of this. So in practice, what we're doing is we're assuming the opposite of what we want to be true. For example, here we're going to let we're going to try to prove that the square root, we're going to prove that the square root of 2 is irrational. It's the big famous example. And in order to prove the square root of 2 is irrational, we're going to assume otherwise. We're going to assume it's rational. And then we're going to show that that leads to a contradiction. Okay? And again, I'll give an example. And this is one of the harder things that we do here in this class. So don't feel bad if it takes you a couple times looking at it, because it's not an easy thing. Whether or not it's simple is another question, but it's certainly not easy. Okay, so let's just start. So does everyone remember what a rational number is? A number is rational if a positive number is rational if there exist positive integers p and q so that x equals p over q. So some examples: 1 over 2, 5 equals 5 over 1, so there do exist those numbers. What about 0.333333 repeated? Is that number rational? Yes or no? How do I do the bar? There it goes. Is that number rational? Bueller, 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 Bueller. Hey, my head's disappearing. I'm waiting for someone to answer me. Okay, I'm done waiting. Yes, that number is rational. Why? Because it's 1 over 3. How do we feel about that? 1 to 5. The definition, how do we feel about the definition of what a rational number is? 1 to 5. Okay. So a number is rational if there exists, let's see, can I go to this halfway? Yes. Okay. A positive number is irrational if it's not rational. Examples: pi, e, and the square root of 2. So in 300 BC, actually before, Euclid wasn't the first person to prove this, but Euclid kind of gave a cleaner proof of it than anyone else. He showed that this number was irrational. He wrote a nice little proof of it. So we're going to prove it. Excuse me for one moment. I'm going to stop my head from going away, from being transparent here. Okay. Yes. Okay. So he proved that the square root of 2 was irrational with this beautiful proof. Okay, so let's do it. So I want to prove that the square root of 2 is irrational. And of course, what we're talking about here is is proofs by contradiction. So I'm going to do a proof by contradiction. I'm going to say the following. I'm going to say, assume otherwise. So I'm going to assume otherwise. Okay? In other words, and I have to do something, I have to do a sound effect. Assume otherwise. Right? So if I assume otherwise, okay, that means the square root of 2 is rational. Assume otherwise. Assume that the square root of 2 is irrational. Well, if the square root of 2 if the square root of 2 is rational, So if square root of 2 is irrational, it has a form, p over q, where p over q are both integers. And it's reduced, right? So what do I mean by a reduced fraction, right? Is 2 over 4 a reduced fraction? No. Why? Because it's 1 over 2. So, I could divide both the top and the bottom by 2, and I get something more reduced. How do we feel about that, 1 to 5? That these things, that if I have a rational number, that means I'm going to have a reduced fraction form. How do we feel about that, 1 to 5? Okay. All right. So, and I'm going to call that thing p over q. Fractions have reduced form. So a reduced form, so p over q So p over q is the reduced form, means that there's no integer n greater than 1, so that n divides both p and q. Okay, so that's what it means to be reduced. Yes, I know my head is in the way, that's why I moved it up. But when I'm writing on the board, my whole body's in the way, so now it's just my fat head, not my huge fat behind. I want to say another word, but now we're online, so I can't. Anyway, so I've got this reduced fraction form for it. Well, that means that if square root of 2 equals p over q, I can move the 2 over to the right, and that means q times square root of 2 equals p. Okay? So I just multiply both sides by q. Excuse me. Okay. But that means, and then I'm going to square both sides. So that means that q squared times 2 equals p. And that means that p is even. Which means p squared is even. How do we feel about that? That p squared has to be even. Right, I've got a number and I'm multiplying it. I've got, yes, even as in 2, 4, 6, 8, 10, 12, right? It's divisible by 2. Well, how do I know? Because I took an integer and I multiplied it by 2. Ooh, that should be squared. I'm sorry. So which means that p squared has to be even. Okay. Well, if p squared is even, can p be odd? What is an odd number times another odd number? If I'm multiplying two odd numbers, is the answer odd or even? Right. So that means p must be even. Okay. Well, if P is even, what's the definition of an even number? Well, if P is even, then P over 2 is an integer. So I've got P over 2 equals N. So that means right, I multiply the 2 over by both sides, and I get that P equals 2N. How do we feel about that? 1 to 5. Okay. So I have an even number, right? So that means P over 2. Right. So I created this number P over 2, and I called it N, right? And N is an integer, and that means that P equals 2N, right? I multiply the 2 by both sides, and then I get the following. Well, if that's true, then let's take this above line. That worked. What happened? I haven't done this yet. Oh, it kicked me up a page. Sorry about that. Hold on a minute. Put back on the geeky glove. Okay, that stops it. Okay, so we take this statement up here. Oh, happy days. Okay, so aside from the annoying blinking, is everyone on board? Okay. All right. Well, so q squared equals 2n squared. What does that mean? That means q squared is even. Okay, the reason why you're saying that the thing looks blurry and the fact that it's not so much blurry, it's the fact that this thing is my pen screen thing just died again. Again, I ordered a backup. Um, but the backup will be here on Friday. So the tablet basically just died again. So that's to the tablet, and now it's blinking at me and trying to cause a seizure. So it's being mean to me. So yeah. So we'll restart the tablet because that's the only way to fix that problem and continue with the regular computer. So what's my problem? I've just said that both P and Q are even. What is the problem? Anybody have it yet? Bueller? Somebody's got it. No, it's not that I don't know what N is. I don't care about N. I just said that both P and Q were even. Why is that a problem? Now, earlier what I said was if P was odd, then P squared would be odd. But P squared is even, so that it's a good question. So because P squared is even, then P must be even. X is even. I just said both P and Q are even. What's the problem with that statement? It doesn't mean that the square root of 2 must be even, but you're close. Yes! Yes! We have a winner! We have a winner! Right? But I said P over Q was in reduced form. Therefore, both cannot. Therefore, how do we feel about that 1 to 5? The question is, the thing that starts with that's reductio ad absurdum. That's Latin for, well, you can't do that. It's absurd. Reduction to the absurd. Okay? No, you don't need to know that. Proof by contradiction. I've reached a contradiction. All of those are perfectly good statements. Okay. It's weird, isn't it? Especially the first time you see it. I've just assumed that the thing I wanted to prove was false. Okay? And I've come up to be, is the these supposed to be them? One of them, yes. Okay. All right, it's a weird thing. It's a weird thing to say this, okay? It's a weird style of proof. And I wish I could be there to see your faces, because then I know how weirded out you are. I'd also, I'd be able to, talk to you about stuff and other things like that. But, of course, we're not together. But it is strange. But it's cool. It's really cool. Let's do another one. Let's do Rawls Theorem. Okay, that's kind of where we're from. This is from the calc book. The proof of the calc book's a little bit different. Let's see. Let's pull up Rawls Theorem here. Because I'm lazy, I don't want to type it out again, and because I'm almost out of time already, let's just do Rawls Theorem right here. Oh, I need more of Rawls Theorem. Let's pull up Rawls Theorem off the old thing here and put it right here. There's Rawls Theorem. All right, let's get rid of some of this. So, we don't need you anymore. We don't need you. We'll get to the proof in a moment. So, Rawls Theorem says that if blah, 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 the top bit is blah, 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 blah. I don't care about any of this. If f is continuous on the closed interval AB, and f is differentiable on the open interval AB, and if f of A equals f of B, then there must exist some point in the middle, some x value in the middle, so that f prime of u equals 0. And you can see that right here, right? I went up, and then I came back down. And because it was differentiable, right? When I went up and came back down, I had to be, fairly well behaved. So if I went up, I'm not sure you can see this. If I go up and then I come back down, okay, I had to be somewhat well behaved, and there had to be a point in the middle where there'll be some point in the middle. There'll be some place where the tangent line is 0. How do we feel about this statement 1 to 5? Oh, thank you. I want to say your name. The person who said refresh in Twitch and it'll stop being blurry, thank you. I don't want to say your name on Twitch. So anyway, thank you. I wouldn't have known to do that. But Twitch is new to me. I'm racking up the achievements on Twitch, but it is new to me. Anyway, how do we feel about this statement? Somewhere in the middle. Why does this have to be true? Let's assume otherwise. Well, assume otherwise. Assume that such a point does not exist. Okay. Now, let's look at this. Since f is continuous, on a closed interval, I know f must have a min okay? So since I've got something that is continuous over a closed interval, oops, that's not ferment, that's extreme value theorem. How do we feel about that, 1 to 5? What do you want, the statement of the whole thing again? Could I get, out of the way? Okay. So I have this thing. I've said that by the extreme value theorem, there has to be an absolute min and an absolute max. Okay. Where are they? Well, if the minimum was in the middle, that would mean that the derivative at that point in the middle is 0. So the min must be an endpoint. In other words, I can't do this, right? I can't have a minimum in the middle, because if the minimum is in the middle, then the derivative of the minimum equals 0. So the minimum must be at one of the two endpoints. I must have something that looks like, this or something like that, right? I have to have something that looks like this. So min cannot be in middle. But by the exact same argument, the max can't be in the middle, right? So the max must be an endpoint. If the min is in the middle, then the derivative at the point is 0. Okay? So the min must be an endpoint. But by the same argument, the max must also be an endpoint. Otherwise, by Fermat's stationary point theorem, the max would be in the middle. How do we feel about that, 1 to 5? Okay. But what does my function look like then, right? Right? If the min, but f and a, but what's true about this thing? F of a equals f of b. The two endpoints have the same y value. Okay? But f of a equals f of b. So the max equals the min equals f of a equals f of b. So what does this function look like? It has to be a constant, right? The max is equal to the min. That means that my function looks like this. But if that's the case, what's true? If it's the case that the max equals the min, and I wind up with this little line, what's true about the derivative? One to 5. I'm getting some nice emotes. How do we feel about that? 1 to 5. Yeah, it's a weird one. It's cool. It's kind of slick. Okay. I'm pretty much out of time. I've got another 3 minutes. We've stated what the yes, full on mental, no cap. Okay. So yeah, it's a very slick proof. It's a very cool proof. As I said, 20% of you are going to be like, yeah, and 30% of you are going to be like, okay, maybe we'll get more this time. But it's a very, very cool proof. So we need to state the so we need to state the mean value theorem as well. But to state the mean value theorem, all we need to do is a little copy and paste of Rawls theorem. So let's state the mean value theorem. Well, here's where we had Rawls theorem. So let's do a little, oops, nope, I don't want to do it. I don't want to move it. I want to copy it. So let's take this little piece here and let's hit copy. And let's come on down and let's hit paste. Not there, where I wanted it. Fine, I'll drag it. I don't know why this worked last time and not this time. Come on down. There we go. And we want to call this the mean value theorem. Why wouldn't it let me type? There it goes. It still won't let me type. It's resisting the idea that I can be able to type. There we go. So in order to do the mean value theorem, is there anything really special about this slope being 0? The answer is not really. I could have had any other slope. And the point is that somewhere in the middle, I have a point that's equal to the secant slope. We should call this Cauchy, because it's his theorem. And Cauchy's mean value theorem says basically the exact same thing, except I'm going to get rid of this condition here. But then I don't get 0. I get the slope of the secant line. I get f prime of u, oops, not there, equals f of a minus f of b over a minus b. I don't know why it does that. And that happened last time too. There we go. So that's the only big change for the mean value theorem. How do we feel about that 1 to 5? How do we feel about that statement? Yeah. I need macros. I need to set up some macros. 1 to 5. Boom. You know, it needs to be like the 3 button on my computer. I need to like program the function buttons. Those big 1, 2, 3, 4, 5 function buttons at the top of my keyboard. I need to program one of them to be 1 to 5. Okay. Any questions? Of course, we should put any questions? Of course, this is Cauchy's mean value theorem. We should probably have a picture of Cauchy up there, right? Let's put a picture of Cauchy up there. Nope, not there. You want a period there. I'm going to drag you up right there. And then I'm going to get out of the way. Oh, there we go. A little bit higher there. Okay. Any questions, comments, issues, suggestions, and thoughts? Okay. So my time's basically up. I went 2 minutes over. So today we went over stop packing. I'm just kidding. I can't hear you pack, which is nice. Okay. I also can't hear you leave because I turned off that function. What we went over today was proof by contradiction, and we stated the mean value, Rawls Theorem, and we stated the mean value theorems, and we wrote, yes, Zach, yes, unnamed person who's on the thing and whose name I did not mention on Twitch. I will scroll it back down. So we mentioned today the mean value theorem, and we did Rawls Theorem, and we mentioned the Rawls mean value theorem. And peer leading on Friday, you will be doing the intuition behind the mean value theorem. And then on Monday, when we come back, we're going to go over and we're going to just kind of fill in some of the little blanks that we've left behind because I moved rather quickly through 2 of the sections. And then, so on Monday, we're going to do some filling, and then I'll talk about new topics. Are there any other questions? Okay. Don't forget that this evening at 5 p.m. is the problem set session. Problem session, we'll be going over problems. I'm going to take off the stupid glove now. And then on Friday is, of course, peer leading and 5 p.m. Eastern, yes. And don't forget that on peer leading, there's also the 2... there are 2 pre-assignments this week, and there's also a web assign boo both tonight and on Thursday. And I will see everybody on, if I don't see you on Friday or at the problem session this evening, I will see everybody on Monday. Also, don't forget that I've got office hours right after this. Any other questions, comments, issues, suggestions, thoughts? Oh, I got questions going on. Did I find an alternative to the Nagel lecture yet? No, I have not, but I found one. I just haven't posted anything about it. But I will post stuff about that hopefully this weekend, maybe next weekend, as soon as I get everything together for it. Good question. Any other questions? I saw other people typing, and then they suddenly decided not to. Okay, so what I'm going to do then is I'm going to turn off the stream. I'm going to jump back into Discord. I'll answer any questions you might have that you want to ask over audio. And then, do we need a webcam for peer leading? No, voice chat will do. But install Discord on your phone, so you can also take pictures while you're chatting over the computer. So you can take pictures of your worksheet. Okay, so I'll answer any questions that y'all have in Discord. I'm going to stop streaming.